Yeah, I've been standing here doing nothing. All right, so we ended last time, right? We were talking about the double integrals, right? We were doing type 1, type 2 regions. So that was 12.2, and now we're going to get into 12.3. So everybody kind of ready for that? Got your notes? There we go. Day14, Day16. Yeah, it was 10, 11. I know, it's like we need something. It's too quiet. All right, so double integrals in polar coordinates. So just a quick show of hands. How many of you saw polar stuff in Cal 2 or in Cal 1? Polar coordinates. A little bit? Just a little? Okay. I kind of act like you maybe have seen it before, but maybe didn't really treat it completely. I'm not going to give a complete treatment on polar coordinates, but if you look at this and you're like still really confused about what polar coordinates are, I recommend you open up your book, look up polar coordinates in the index and do some research, Google it, whatever. I do an okay job of at least introducing the concept. So before we get there, this is a review of the 3 types of regions that we have up to this point, right? Those are the 3 types. We have the rectangle, which we called R. That's where your A and B are between constants, your C and D are between constants. We have type 1, where your A and B are between constants. I say A and B between constants. That doesn't make any freaking sense at all. Your X's are between 2 constants, A and B. Your Y's are between 2 constants, C and D. Here, your X's are between 2 constants, A and B. Your Y values are stuck between 2 functions of X. Type 2, your Y's are stuck between C and D, and your X's are stuck between 2 functions of Y. Right? That's what we did. Now, it's necessary. Where's that slide? Oh, we are going to investigate some regions which force us to possibly use a different coordinate system, because there's more than one way to look at 2-dimensional space. So remember that if you're given any point out in space, so imagine this circle's not here and this triangle's not here. If someone just picks a point in 2-dimensional space, we call that XY, right? But that's using what we had always referred to as the Cartesian or rectangular coordinate system. Rectangular coordinate system says, imagine this is the ground and you're standing there, right? And you want to walk to that point. One way you could do it is to walk out this way, right? Certain distance, X, turn 90 degrees, right? 90 degrees this way, and walk a certain Y value to here, and that's how you get there. But that's not the only way you can get there, right? You could instead say, instead of going out and taking a 90-degree turn to the left, you could say, instead of aiming that way, aim a certain angle and walk a certain distance, and you'd still get to the same point, right? Oh, that's me. So to get to this point in rectangular coordinates, you need 2 things, right? X and Y. To get there a different way, by doing a turn and walking out a distance, you still need 2 things, right? What do you need? How much to turn by, and then how far to walk out. So this still requires two parameters to get to that point, but they're different, right? They're completely different concepts. So here, if I change the R, right? Change the R, it's going to change how far out I walk. If I change the angle, I change the angle. All right. So this is what I'm saying basically to you right here. Instead of moving out X and up and down Y, we can turn and go out. That's the idea of polar coordinates. Now, if we do that, we create a relationship between Cartesian and polar coordinates. So what's Cartesian? Cartesian is xy, right? Or in three-dimensional space, Cartesian is xyz. So how do we convert from Cartesian to polar? Well, by looking at our triangle here that we create, we have the Pythagorean identity that says x squared plus y squared is r squared. So that's our first relationship between the x's and the r's, x, y, and r. And then by the definition of cosine of theta, cosine is adjacent over hypotenuse, so you could create this relationship that x will always be r cosine theta. And then you could do the same for y. And then this theta here comes from the relationship between theta, opposite side and adjacent side tangent, right? And then do the inverse on both sides to get back to theta. So those are the major connections between Cartesian and polar. If you start in Cartesian, there's a way to get to polar. If you are in polar, there's a way to get back to Cartesian. So it's almost like everything we've been doing right now up to this point has been with our Cartesian goggles on. And what we're going to do is we're going to take them off and we're going to put on our polar goggles and we're going to look at the world of two-dimensional space in a completely different way. All right? So remember, for rectangular, when we said rectangular back in Cartesian, rectangular meant that our x's were between two constants, our y's were between two constants. Now remember, x and y in Cartesian are our two parameters, right? X and y. But what does rectangular mean in polar coordinates? Well, rectangular still means our two parameters are trapped between constants. So the two parameters we have in polar are theta and r, right? Theta and r. So if I trap my theta between two constants and I trap my radius between two constants, what does that create? What does that look like in two-dimensional space? Well, it's not a hidden thing, right? Can you see it on yours? Oh, I didn't. Did I actually give you an example? I did give you an example, yes. Okay, so look, A and B here is my radius. I'm changing my radius. So what's happening here is that, notice that everything in that blue region, if I look at from here, from the origin out, what I'm saying is every point in here is bigger, has a radius that's bigger than this arc, right? And smaller than this one. So my radius is trapped between two values. And then my rotation angle is trapped between two values. Do y'all see that? Now I can also change my angles. I could do that, right? My theta is still trapped between what? It looks like it's between here, this angle, and then out this way like that. And my radius is still stuck between those two values. Now, what's valuable about this? I mean, why is this an important concept? What type region is that before we started today? Okay, if I walked into class today and I said, what type region is that? From last class, or the last two classes. You wouldn't be able to really tell me what type of region that is, right? It's not, okay, it's not a rectangle. In Cartesian, it's not rectangular, right? That doesn't look like a rectangle. Okay, is it type 1? Well, maybe part of it. You'd have to start cutting it up into pieces to start to try and make, okay, like if I cut it right here, right, then I could look at that little piece as maybe a type 1 or type 2. Well, you'd have to mess with it a little bit, right? But it's complicated. Do you see that? It's a complicated region if we just are stuck with the three we had from last time. But in polar coordinates, this is technically a rectangular region, meaning that it's just our two parameters stuck between constants. And when we did double integrals initially, didn't we love when our x's were stuck between two constants and y's were stuck between two constants? Because the integral was pretty easy. In fact, we could even switch the order of integration and it didn't even matter. So we like rectangles, but what we need to get our heads around right now is that a polar rectangle looks like that. Okay, polar rectangles don't look like rectangles. So if someone now, you know, if you were to walk up to a 4th, 5th grader right now and say, draw a rectangle on the board, right? They walk up there and they go like this, right? They're like, there's a rectangle. And you're like, no, you know, this is a rectangle. They're both rectangles, right? This is a polar rectangle, this is a rectangle in Cartesian. So they look different. All right, now why is that going to help us here? Well, if we can get our regions to be polar, then our double integrals should involve constants on the limits of integration. But we need to talk a little bit more about how we're going to develop the integral. This is real important here. Back when we set up, in Cartesian, when we set up the double integral, right, this little dA out here was our dx dy. Or, oh, is that copied? Is that actually printed out in the, that stupid keyboard? I hate that damn thing. I can't disable the damn keyboard on that. I have no choice but to leave it. All right, well, that's either a dx or a dy. Where did that come from? Well, what we were doing was we were looking at the Cartesian plane. X's go out this way, Y's go out this way. And we said, okay, just let X change a little bit, right? We'll do like an infinitesimal change in X. That'll be the width of the base of the, remember, we're going to make that rectangular solid, add them all up to get the volume underneath. Do I need to go to that picture? You know what I'm talking about? Yay or nay? Looking at me like I'm, yeah, where you add them all up. It was a Riemann sum, right? But we were doing Riemann sums of these like towers instead of rectangles. (12.1.2) is where it is, okay? 12.1.2 is where it was in our notes. So the base of that tower was an infinitesimal change in X, and then the infinitesimal change in Y. Now, those two, the dx and dy, are perpendicular to each other here because we're in Cartesian. So the x and y are perpendicular, so our change in x and change in y are perpendicular. So it made perfect sense to call that little yellow spot dA, area, length times width, right? So the area of that yellow is just dx times dy, which is our dA. Now that may seem trivial, we've already done that. But what do polar rectangular regions look like? So did I pass it up? There it is. Now, this is what I'm saying is important. Do you agree that all these little pieces here that I have, right, all these little pieces, aren't all of those rectangles? They're all polar rectangles. So this is exactly the same as this picture here. It's all those little rectangles everywhere, but because we're in polar, that's what they look like. So the question becomes, what is the area of that red? Because that red, what I'm going to do is I'm going to take this red and I'm going to build a tower on top of it. So I'm going to stack it and then I'm going to add them all up, right? So it's still a Riemann sum. So I want to take a double integral over that region. I'm going to have a function of r and theta instead of x and y. But my dA is different than it was before. It's not dx dy because we're in polar. So I just need to figure out what that area is. Does everyone agree that this side right here, this side of this, is dr? Because remember, the inside is my radius, right? And I'm going to change it just a little bit infinitesimally and go out, and that'll be my change in radius. So I slide it out a little bit and get this. Yes or no? I mean, yes? Okay. Now, this is the tricky part right here, this part. Because this part right here is not theta. Okay, that's not theta. This is like the length of an arc, isn't it? An arc length, isn't it? Right here. Now theta is this angle. So what's happening is I'm changing radius just a little bit, and I'm changing theta infinitesimally. And when I change that theta, I swing through that red part, and I say that it's r d theta. Why is that length r d theta? That goes back to pre-cal. In pre-cal, you were given a formula that said this. If you take a slice of pie like this, if this is r and this is theta, and this is s, which is the length of that side, it's the arc length, or the length of a sector, that s is equal to r theta. Now, in that formula, there was something that had to be stressed to you. Hopefully it was. What is the thing we have to always make sure about theta if we're going to use this formula? Remember? It has to be in radians. This formula does not work if you use a degree there. So, for example, what is the circumference of a circle of radius r? If the radius of a circle is r, what's its circumference? Well, you go all the way around, don't you? You go all the way around? Instead of this one up here where it's just that part, I want to go all the way around. So what's r in this one? Well, just r, right? What's the angle I turn through? 2 pi. So s should be r times 2 pi, which is just 2 pi r, which is the circumference of a circle. So this formula up here is actually, from pre-cal, a more general formula for finding arc length of a circle. In case you forgot that, that's okay if you did. Coming back here, though, do you see that little picture again now? So that right there is like the S. And so the length of that should be the angle times the R. But what's the angle? It's d theta. It's how much the angle is changing by. So that gives us this r d theta. So that is why our dA turns into r dr d theta or r d theta dr. Why? Why the heck is that? Why is it that I'm taking r d theta right here and multiplying by dr to say that that's the area of that? Because, I mean, does anyone have a problem with that? Am I the only one who has a problem with that? That's not a rectangle, right? I mean, it's a polar rectangle, I get it. But I'm saying that if I multiply those two, it gives me the area of that. Why is that okay? Or well, forget that we're in polar again, okay? And I come here right now and I draw a rectangle up here and I say, all right, everyone, this is 3, this is 2, what's the area? 6, right? So what if I do this and I say this is dr and this is r d theta, then what's the area of that? r dr d theta, right? But this is a rectangle, isn't it? And the area of a rectangle is the length times the width. That does not look like a rectangle. But why is it okay? This is a critical thing with calculus that you have to kind of get your head around. I don't give anything. I thought I had a demonstration of this. That's exactly why. Because infinitesimally, what happens is, as this gets smaller, right, as that little red region gets smaller, because dr is an infinitesimal, and d theta is infinitesimal, what happens is the smaller that gets, the closer it gets to becoming a rectangle. So in the limit, as you go to infinity, that object becomes a rectangle. There's less and less error, right? The smaller it gets, there's less error. And so as you go to infinity, the error goes away and it becomes okay. So that's exactly what it is. And we do that a lot in calculus. So I just want to make sure I point that out. All right, so that gives us our grand formula for polar integrals. Double integrals over polar regions. If our region R is a function, if our region is all the points r theta, notice it's not xy, right? It's r theta, where theta is between alpha and beta. Alpha and beta is what we usually use to talk about angles. And our radius is between a and b. Then the double integral of some function of xy dA now becomes this integral, this double integral. So let's see what happened here. X became r cosine theta. Why? That's what x is, and when you convert x to polar, that's what it is. What does y become? R sine theta, right? And then I have r d theta dr. Where'd that r come from? That's what dA was. Remember dA we just said was, dA was r dr d theta, right? Does the order here matter, do you think? D theta dr, my thetas here are on the inner integral, and those alpha beta go with the theta, right? R was the radius, that goes with A and B. So do you think that order matters? It does, but we can flip it though, because they're constants, because it's a polar rectangle. But if we flip dr d theta here, what do we have to do? We have to flip the integrals also. So limits have to switch. Okay, and I put here, notice R in the formula. In my years of teaching this class, that's the thing that gets left out. People forget the R in the formula right there. All right, here we go. No. R is our variable, right? dr d theta. So R will be like X was for us before. That's why it's important not to leave it out. All right, so let's take a look at this problem. Find the volume under z equals 3x plus 4y squared on the region bounded by... Good question. Let's talk about that, because that's what I'm doing. I'm going to bring this up. And I'm going to say we want to find the volume under z equals 3x plus 4y squared on the region bounded by x squared plus y squared equals 1, x squared plus y squared equals 4, and y is greater than or equal to 0. So let's start with our region, right? Start with our region. Maybe we try and draw it. I hope that you recognize x squared plus y squared equals 1 as a circle, right? So I have a circle, radius 1, and it's the entire circle, right? And then I have a circle radius 2. Yes. Well, I don't know. I mean, maybe at some point you'll look at the circles, and as soon as you start seeing circles, you start thinking polar, because polar comes from the idea of a circle, right? You have a pole, and then you go out a certain distance, and you rotate around. So everything has a circular kind of look to it. Like the polar rectangles all look like portions of it looks like part of one of these sections, right? All right, now there was one more condition. Y had to be greater than or equal to 0. Yeah, so that cuts everything off the bottom, right? So that means you've got everything in here. Now, could you stick with last class and try and look at that region as a type 1 or type 2? So let's try type 1 for a second. Type 1 would mean our x's have to be between two constants, and our y's would have to be between two functions of x. So look at this. I agree that up here, you've got kind of like an upper function of x. But on the bottom, it's kind of weird, because what happens is right here and right here, what's on top and bottom is different, right? On this one, on top is that circle, right? On the bottom is what? 0. Y equals 0. And then over here, between there and there, the top is the circle and the bottom is the little circle, right? And then the next one, so you would have to do 4 different double integrals here. Wouldn't you split it up? What about symmetry? Yes or no? We talked about this once before. It depends on this. Because remember, this is just the ground. So when you look up above that, what does it look like above that? Because in order to double it, you have to promise me that what's above it is symmetric. And I don't recall this example, but yeah, I don't think it's symmetric. Let me see. Yeah, that's not symmetric. See, if I look at it from the top like this, right? There's my little region. But if I come in here and look at it from the side, it looks like it's really stacked heavily on the right side, right? I get a lot of volume on the right side. Left side, I actually get some negative volume. So it is not symmetric above. And since I don't really have a good, easy way of determining symmetry, I am never going to assume symmetry on the function that I'm integrating. I kind of led you right into that one, sorry. But it's important that we keep that in mind. I don't want anyone putting, trying to use symmetry on this problem. Yeah, the only way is if you're integrating a constant. Or, I mean, that would be easy, or if you knew somehow it was symmetric. All right, let's talk about this now. I don't want to split this into 3 different double integrals, right? But it's a perfect polar region, right? I mean, it doesn't get much better than that when it comes to polar. If I started out at the origin, I look out to the right, I'm going to rotate through what angle? 0 all the way to what? Pi. And my radius is stuck between where? 1 and 2. So everything in that yellow, my radius is between 1 and 2, and my angle is between 0 and pi. Yes? So what I note here is that for this, R is equal to the set of all points R theta such that theta is between 0 pi and R is between 1 and 2. Is it stuffy in here? Like really stuffy? Yeah. So the double integral can be set up. My double integral over this R of f of x, y, dA, now being turned into a polar double integral, becomes double integral. Now my limits of integration are going to start with what? Let's go A and B. So 1 and 2. Then alpha beta, 0 pi. And then the function evaluated at, well, it's supposed to be 3x plus 4y squared, right? But what's x going to be converted to if we go polar now? R cosine theta. So instead of writing 3x, I write 3r cosine theta. And instead of writing plus 4y squared, I write plus 4, what's y? Y is r sine theta. So r squared sine squared theta. Does everyone see that this is 3x plus 4y squared using our conversion from Cartesian to polar? Now, R, do not forget that R, right? That's the R that needs to go in there. So R, yeah, it looked like a square root. R, and then D what? D what? D theta dr. What are you going to do with this? Throw in the calculator. 1, 2, 0 pi. Go ahead and distribute that R through. 3r squared cosine theta plus 4r cubed sine squared theta d theta dr. So I guess you could say there's always going to be an R that's going to distribute through, because that R is always going to be there when you convert from Cartesian to polar. How would you do this in double integral? I mean, would you go right now and just try and do antiderivatives? I mean, you could, right? I mean, you could try, because you're going to first take the antiderivative treating theta as your variable. So all this junk is just a constant. What's the antiderivative of cosine theta? Sine theta, right? What's the antiderivative of sine squared theta? Yeah, first you have to switch this over right here. If you're going to do sine squared, you have to do a power reducing formula first. Remember that? So 1/2 minus 1/2 cosine 2 theta. Now you integrate that. But we could do it, right? Another way you could do it, I don't know if anyone recognizes this. This is like two completely different integrals, right? Because there's a plus sign between them, double integrals. And if I look just at this first one, don't I have, my two variables are r and theta, aren't they? Aren't my r's and thetas completely separated from each other with multiplication between them? Yes? And we had a property, I'll point it out. I'll tell you where it is. If you flip to 12.1.6, it was a special case we had for double integrals. It said if you're trying to take a double integral and the function inside here is a function of two variables. Now in here, in this, it was x and y. And those two, that function can be split into the product of two functions where your x's were in one and the y's were in the other. Then you could split it up into two Cal 2 integrals where it's just single integrals. So I could have done that too. Either way, in the end, everyone is expected that you could, at this point, take that the rest of the way. Do I need to, or? I mean, all the fancy stuff's already done. We converted it from Cartesian to polar. Now it's just integration from here. Feel like you could do that? I don't know what these looks I'm getting are. So I'm going to proceed, or? I'm losing everyone, aren't I, huh? I lost you a long time ago, I guess. Let's look at 12.3 example 2. Find the volume bounded by the paraboloid z equals 4 minus x squared minus y squared and the xy plane. Z equals 4 minus x squared minus y squared and the xy plane. Again, I'm going to act like I don't know what this looks like. Z equals 4 minus x squared minus y squared, right, is a paraboloid. So at this point, you kind of have to know what a paraboloid looks like. So you might need to go refresh yourself a little bit on the quadratic surfaces that we covered way back in chapter 10. But you can also just plug in some points and try and figure out what this looks like three-dimensionally. Like, if x and y are both 0, so if we're at the origin, this is x and this is y and this is z. If we're at the origin, what's z? 4, right? Okay, what if y is 0? What if y is 0? Completely, it's gone. So that means I'm looking on the xy plane only. If y is 0, z equals 4 minus x squared. Isn't 4 minus x squared a parabola that opens down, that goes through 4 and then hits where on the x-axis? Where would it hit? 2. So it looks like this. And then it goes back the other direction too. And what if x is 0? Same thing, right? Except you got parabolas in the yz plane, so it would look like this. And then if you put everything together, you get this paraboloid. Now I want to know the volume between that paraboloid and the xy plane. Now the xy plane is the same as saying what? Z equals 0. So I'm trying to find now, where does this paraboloid hit the xy plane? Well, that hits where z is 0. So put 0 into this up here. Replacing 0 or z with 0, we get this. Move the x squared y squared to the left, and you get what? Circle, radius 2, that lives on the xy plane. So, of course, that means you have a circle down here, right? So now let's talk about setting up your integral. This right there is your region, right? That's what you want to integrate over. And that means that your region is a circle, right? Radius 2, right? Isn't this region perfectly suited for a polar region, for a conversion to polar? Could you do it as a type 1? You could. Could you do it as type 2? Yeah, but you would have to, again, cut it up into pieces. And we can avoid that completely by doing everything in polar. Questions? So can we write out what this region is? It's the set of all what? R theta, all points R theta, such that theta is between and R is between. So what's theta between here? 0 to pi. And R is between what? 0 to 2. One of the mistakes that I've seen on this is to say R is between -2 and 2. I've just seen students do it before. Generally speaking, our R is always going to be positive. I'm curious though, could you still create this region with going from R equals -2 to 2? Then your theta would go from 0 to only pi. It's one of those things, what you have to imagine is if I'm here and I want to walk, if I say, look, your theta is, let's say, pi over 4, so I'm aimed this way. And I say you're allowed to walk out 2 and -2, then you go backwards 2, then you can take up all of that. And then if you rotate some more, you know, you start doing this, rotate some more, you do that, that. And so you see, you can actually create the whole circle by only rotating by pi, but walking 2 and -2. That's a little bit too, like, we don't need that. Just 0 to pi, 0 to, we're done. Do you follow that? Okay, so what's this double integral going to look like then? Double integral 0 to 2, 0 to pi. Now, what are we integrating? What's the function on top here? What's the cap of this solid, the top part of it? 4 minus x squared minus y squared, right? But I need to convert my x's and y's over. So this is 4 minus r squared cosine squared theta minus y squared r squared sine squared theta. Then r, thank you, d theta dr. Oh yeah, we're cleaning that up. We're going to factor out a -r squared from the second two terms there. We're going to factor that out, a -r squared. If we factor a -r squared out of just those two terms, we're left with a cosine squared theta plus sine squared theta, which is 1. Right? We want that, right? We want that simplification. Then we still have the r out there. Then we could distribute the r through. And now we're integrating with respect to theta first. Theta doesn't even appear anymore. So that'll be an easy integration. We just go back from there. Questions? I'm not looking at that. I'm actually thinking of the problem that I'm going to put up here now, but it looks like I'm just staring at that now. Dreams. Yeah, you made me look at that now. I'm like, all right, let's definitely get back to work here. I don't. It's just so you can see it from different angles in the room. Yeah. Well, apparently we all. I mean, I'm daydreaming about it apparently, so it's working. Okay, how about this? I'm making this problem up. Sorry, it's not in our notes. Using polar double integral, show volume of a sphere, radius r, is, what is the volume of a sphere? 4/3 pi r cubed. And let's make that capital R, because I think that might confuse people later with our polar. Let's make it a capital R. Who knows what we're going to do? Close. Actually, we will be able to do that, but not till we get to a triple integral. Remember, the double integral of 1 gives you the area of the region you're integrating over. The triple integral of 1 will give you the volume of the three-dimensional region we're integrating over, but we're not there yet. Okay, so x squared. Okay, we have a circle. That's the floor. Okay, so if you have this sphere, you're saying it has a radius capital R, then the circle where it crosses the xy plane would be x squared plus y squared equals capital R squared. Yes. So that's our floor. What's the cap? Capital R. Okay, so what we're going to work is just like we did with the paraboloid just a second ago, except instead of the paraboloid coming down onto the xy plane, we actually have the sphere coming down onto the xy plane. So let me write down the equation of a sphere, which we all know, right? Centered at the origin, radius capital R. That's the equation of a sphere. General sphere, centered at the origin, capital R is its radius. If I'm going to look at that as the top, as my surface, I have to solve that for z, don't I? And if I solve that for z, that means I have to take a square root at some point, which means I'll have a top and a bottom, which is fine because I'm only going to look at the top. And I will be able to double the answer in this one because symmetry of the sphere. All right, so let me do this. Solving that for z, you get square root of capital R squared minus x squared minus y squared. You agree? My 3D picture is this, like that. Subtract the negative half. Yeah, it's plus or minus. You could, but I'm not even going to look. I'm going to chunk it. I'm just going to say I'm just looking at the top cap. Well, your plus or minus would be here, so that would be in your integram. That's right. We have, z is two different functions right now. This doesn't say one minus another. This says you have two different functions. So which one do you want to integrate? Which one do you want to integrate, the positive or the negative? You can't carry the plus or minus the whole way because then it's hard to explain, but you have, you know, everything was supposed to be f of x, y. Here we have two f of x, y's. So we have to make a choice here. I think what you're thinking is more like if we had, let's say our region was this, that we wanted to integrate over. And let's say it was circle radius 1. The equation would be x squared plus y squared is 1. We could look at the top part of that circle as square root of 1 minus x squared, right? Y equals that. And we could look at the bottom part as y equals negative square root of 1 minus x squared. And then when we do our integral and we subtract, then that subtraction will become addition and it will double. I agree with that because those are our limits of integration. In the problem we're doing now, the plus or minus actually is the function we're trying to integrate. It's not the limit of integration. But we can talk about it more if you want afterward. I'm just going to look at that top half, cut it off at the xy plane, and then I'm going to figure out what that volume is and double it. So what is the region on the ground there? Well, I don't even care about what it is as far as circle necessarily. We can get the equation, but we know the radius of it is what? Capital R, right? And we know to make it polar-wise, we have to swing all the way around. So from that, I can just say that region, now I don't want to call our region capital R because we're using capital R for radius, but I'm going to call it just D, okay, just for a region. This D equals all the little r thetas such that theta's between 0 and 2 pi, right? And our little r is between 0 and big R. Do you all agree? Okay. Then the integral, double integral. Double integral, 0 to, what goes first? Big R, then 0 to 2 pi, then your function that we're integrating, which was this, z, right? But what did we just say a second ago? What is x squared and y squared? That's r cosine theta squared minus r. So I guess what I'm getting at is if I come back up here and take a look at this, this is capital R, check this out, minus x squared plus y squared. Agree with that? But what's x squared plus y squared? Go back to your Cartesian. It's little r squared, isn't it? Little r squared? Go back to your, isn't Pythagorean identity, x squared plus y squared equals r squared? So if I factored it now, then when I come back down here, this is just square root of capital R squared minus little r squared times r, right? d theta dr. I'm going to do this one because I think it's worth seeing the result. All right? Has anyone tried to show the volume formula for a sphere in Cal 1 or 2? Anyone do that? Yeah? It's not this easy. It's not this easy. What's the antiderivative of all of this crap in here with respect to theta? It's just all that crap theta, isn't it? Okay, so my inner integral looks like this. 0 to capital R. I think I want a new page. Okay, I want the outer one 0 to capital R. The inner one became square root capital R squared minus little r squared times R, sitting out here, times theta, evaluated from 0 to 2 pi, and then I have the dr out here, right? Now plug in 2 pi for what? Theta, maybe I should have put that here. Theta is 2 pi, theta is 0. You may not need that depending on how comfortable you are with these. If I plug in 2 pi, I get 2 pi in front of all that junk. If I plug in 0, it's all gone. So all this really becomes is the integral 0 to capital R of 2 pi. Let me move that R out front. It's kind of, I don't like it being behind the square root. dr. Anybody? I lose anybody here? That integration is just a basic substitution. What is the basic substitution I would make? Well, u is capital R squared minus little r squared. The derivative of that is negative 2r dr, which I almost have, don't I? Don't I have right here 2r dr right there? So I'm off by a negative, right? I'm off by negative, so if I were to multiply both sides by negative, it'll become plus. So I'm going to replace everything in yellow up in the integral with what? A negative du, and then I'm going to replace my capital R squared minus little r squared with u. I'm not going to worry about limits of integration. I know some of you are taught to switch your limits of integration now too. I don't. I just do the integral. I switch back. So this becomes, I still had that pi in there, didn't I? I'll just leave it in there. We always pull constants out. I think it's unfair. We can leave them in there. It's no difference, right? And then I have a negative, right? So the negative, shoot, I'll put the negative in front. Who cares? And then I have what? Square root of u. So u to the 1/2 du. What is the antiderivative of u to the 1/2? Negative 2 pi over 3 u to the 3/2. But now switch back what was u, so this becomes negative 2 pi over 3 square root of capital R squared minus little r squared, what, cubed? Oh, yes. Well, no. Yes, it is. But that means square root cubed, right? Yeah. This is just our u. Agree? And I'm going to now evaluate that from where to where? 0 to capital R. What happens if I plug in capital R for little r, right? Little r is our variable. If I plug in capital R for little r, I get what? 0. So I get 0, take away negative 2 pi over 3. Now plug in 0 for little r, and we get what? The square root of capital R squared, which is just capital R, but then cubed, so we get r cubed. And if you do a double negative, it becomes positive, right? So 2 pi over 3 capital R cubed, that was half of it, right? That was half of it. Double that, you get 4/3 pi over R cubed. I like that problem. You can do that pretty much for anything that you can get control of the surface on and see its image on the ground. So cone you could do, you could do a general like ellipsoid. I'm thinking that maybe a different coordinate system would work better. It all depends on what the region on the ground is going to look like, okay? And see, what we also haven't seen yet is a triple integral. Where a triple integral, you're going to have, like with the formula for the integral of 1 is the area, for triple, you're going to have the volume. So sometimes, like we might revisit this one again in triple, where what we do is we just make our region the sphere, and we do a triple integral of 1 on that sphere. But let me think about that. I'm not sure what would be the best way to approach that one. I'll think about it. Okay, let's now move on to the next note, 12.3.8. So the only difference here is that everything that we've done, all the examples that I've done so far, it's always been some like surface and then going down all the way to the XY plane. But if we have a surface on top and a surface on bottom, then the only difference is that your polar region is still the same, but now you have to take the function that's on top and subtract the double integral on the bottom. This is a good problem right here. Find the volume of the solid below x squared plus y squared plus z squared equals 1, and above the cone, z equals square root of x squared plus y squared. So here's your sphere, right? That's x squared plus y squared equals 1. Here's your cone. And we're trying to find the solid between them. Do y'all see it? It's almost like a little snow cone, isn't it? So if you can kind of visualize this, you have a sphere on top, right? We're not looking for the volume of the sphere all the way down to the ground. We're stopping it at some point, and we're saying the thing below it is a cone that comes up. The critical point of this problem is to try and understand what the region of integration is. Because when you look at this straight from the top, your region of integration is not the circle radius 1. The region of integration is where the cone comes up and hits the sphere. And when it hits the sphere, it creates a circle. We need to know the radius of that circle so that we can get control on our region. So how do you figure out where the cone meets the sphere? Set them equal to each other. Or if I already have the equation for z in the cone, all I have to do is take that z and plug it in here, and I should be able to generate an equation that has x and y in it, which would represent my intersection, right? Okay, my battery is getting pretty close. Let me plug in. Why don't y'all try and come up with that region, either mentally or... Oh, it's in the side here. So to figure out where those two meet, you have 2x squared plus 2y squared equals 1, which means x squared plus y squared is 1/2, right? So what's the radius of this circle? The radius is, I'll say capital R. The radius of that circle is square root of 1/2, which is the same as √2/2. I only put √2/2 because that's just something we see so much in math that everyone should know the square root of 1/2 is √2/2. That's it. So I know that looking straight down where they hit each other, I have this circle. This is my region in here, which means that this D, I'll call it D because I'm mixing up R's and everything else. My D should be all my little R's and thetas, such that my thetas are between 0 to pi again, right? R's are between 0 √2/2. Excuse me? No, that was just so everyone knew that I'm just saying the radius of this is that. I'm not using capital R again. I just didn't want to put little r up here and then down here have little r mean something else. All right, so what does a double integral look like? Well, we've got 0 to √2/2, right? Then our constraint on theta. And then our function. Now this is where you have to be paying attention. Which is the function that created the top of this solid? It's the sphere, which means you have to solve the sphere for z, which we haven't done. But it's 1 minus r squared, right? Well, square root 1 minus r squared, right? Because we have x squared plus y squared plus z squared equals 1. Moving things over, you get z equals square root 1 minus x squared minus y squared. But I just did that thing a second ago where I factored out the negative. X squared plus y squared was r squared. So square root, the top of the sphere is the square root of 1 minus r squared. Yes? So square root 1 minus r squared. Now I could right now at this point put r d theta dr. And then come through and subtract another integral that represents the cone. But I like to do it all in one integral because what I'm doing is I'm taking that as the top function. I come through here and I now subtract from it the cone on the bottom. What's the equation of the cone? What is it? Yeah, look at the equation up there. Z was equal to square root of x squared plus y squared. X squared plus y squared is r squared. So the square root of r squared is r. So z is r. The polar equation for a cone is z is r. Wow. Yeah, you can be in Cartesian or in polar when you go about trying to find their intersection. Absolutely. So this means z equals square root of r squared, which means r. This one we saw a second ago was 1 minus r squared. So I'm just going to put r here, and then I can do my r d theta dr. Now, I'll point you back to the note that I just put up right before I did this example. The note says that if you want to do the volume between two surfaces, you just put the two together, right? It's the top surface minus the bottom surface. That's what I just did. I did not want to split it into two separate double integrals. And that's it. I'm just going to box that out. That you can take the rest of the way, right? Distribute that R through, the R that we did not forget. Distribute R through, and then go to town. What's that? Well, not if this R comes through. Did you say make a use of? Oh, yes. Yeah. It would be almost like the problem we just did. Yeah. I thought I heard trig substitution. You don't need trig substitution on that. I mean, if that were the only thing, then you would have to, well, you could either formula the back of the book or do a trig sub on that. And then, well, whatever. We could take it from here, just distribute the R. Could we? I say that like, you know, I've been saying that all semester. You could do that now. I guess when I say, I guess that's the expectation, is that you could do that now from here. All right, next one, or next topic. We're getting close to the end of this, aren't we? Yeah, so far we've looked at a rectangular polar region. You know, and remember type 1 back from rectangular, back in Cartesian, it was rectangle in Cartesian, x was between a, b, y was between c, d. Rectangular and polar, both theta and r between two constants. Then we had type 1 in Cartesian, where our x was still between two constants, but our y was between two functions of x. You can do the exact same thing with polar. You can fix your theta between two constants. So my theta goes from, you know, say alpha to beta, okay? But now your radius is variable. Your radius depends on what your angle is. And if that happens, then you get what would be considered almost like a type 1 region in polar. If you do have a region like that, then here's what your double integral looks like. Your theta is between two constants. Your r is between two functions of theta. And now take careful notice of this double integral. I've got alpha, beta in my outer because it's the ones that are being held constant. The inner one are my variable functions. F of x, y, this is the same thing, converting from Cartesian to polar. I still have the r, but now instead of d theta dr, I have dr d theta. I have to have it that way because my theta is in the outer integral, my inner integral has the r. Question? This is a very interesting problem right here. What happened was I was at home doing this I think it was over spring break. I was working on this, and I started putting together the code to make all that happen, which is all this. And then I realized that I did this like 3 years ago, and I had this picture right here, which was even better than what I had put together here. So I threw them both next to each other. My new version and my old version. I like my old version better personally, but what happens here in this problem is that we have a sphere of radius 3. It's going to have a cylinder of radius 1 drilled out of it, as shown below. Set up the double integral, which yields the volume of the remaining solid. So that green is like my drill bit, right? It's going to come down. Notice that it's not going right through the center. If it was going right through the center, this problem would become much easier. But the problem is it's going through off-center. So that drill bit is going to run kind of tangent to this axis. So it's just going to touch that axis. The center of it's going to go right through this axis. I'm going to drill it out, right? And now after I've drilled it out, I want to know how much is left. I don't remember what I put here. Oh, yeah. This right here is a picture of what's been drilled out, but only the top of it. What I was trying to get at by showing you just the part that's been drilled out, and you can't pick it up too well here, so let me turn that off. What I was trying to get you to see with this is that that is not a cylinder that has had a slice like a plane through it, is it? Because the top of it, and damn it, it's really hard to see. Well, I guess not too bad. But it's rounded off at the top because that's part of the sphere. So a lot of students think, oh, I just need to find like the volume of the cylinder and then just like cut it off or something. Well, it's the fact that that cap is rounded that makes it a lot more challenging. Yes? All right, so let's try and attack this problem. If we look at this problem again from the top, right, if we look at it from the top, we are trying to find the volume by taking this piece out, right? Another way of looking at that would be, we know the volume of a sphere, generally, right? 4/3 pi r cubed. And I know the radius of this is 3. So I know the volume of the sphere to start the problem. Maybe I should approach this by just trying to figure out how much gets drilled out. If I figure out how much gets drilled out, that means I want to find the volume of everything, I guess, below this green thing, right? Everything from that green thing down. So look at your region of integration on the ground. It's a circle, right? But it's offset. Do you agree with that? It's offset. It's not centered at the origin. Well, how do we handle this? So that's why I'm going to walk you through this. Can we all agree on this? Say again? Jeez. No, it's not. That's better, is what it is. Okay? I'll address it, what you're saying in a second. Some students will want to say, you know what, this is a circle, radius 1, right? It looks really different up there than it does down here. I mean, it looks like a just perfect circle on my screen. It's the resolution ratios here. So that circle right there, a lot of people say, well, you know what, let me just shift it all over. The problem is that the surface above it would also have to get shifted over if you're going to do that. You can't just move the region. If you move the region over to center it, then what's above it that you're drilling out is very different than if you were shifted over, right? It's like moving the drill bit. So I'm going to have to force myself to stay here. My circle's radius comes out here like this, right? Now I go mess it up. But just imagine that's that sphere, right? That's the sphere that's capped on top of this. I don't need that there. I just want to remind everyone that's where it is. So I'm going to drill this out. How in the hell can I go to polar here, right? So let's talk about this. This is a circle radius 1, isn't it? But it's centered where? It's centered at 1, 0. What is the equation of a circle radius 1 centered at 1, 0? X minus 1 squared plus y squared equals 1. Now, I'm going to expand this out. X squared minus 2x plus 1. If you've stayed in this class today, you've hung in there. I know I haven't turned the lights back on. That's a little dangerous right now. But if you've stayed around and hung in this long, this is the most important part of today, right here. I'm going to subtract 1 on both sides, okay? And I'm going to recognize that when I go to polar, x squared plus y squared is what? R squared, isn't it? Isn't that r squared? I'm going to switch this equation of a circle to a polar equation right now. X squared plus y squared is r squared. And what is x? Is r cosine theta, right? So what I have now is minus 2 cosine theta equals 2r. Yes, forgot my r. R cosine theta equals 0. Equals 0. Now, if we can get r to be a function of theta, going back to this note right here, if your radius, how far out you are, is a function of theta, right, then we can use this new double integral. I just need to figure out how I can get a function of theta, basically. Going back to this. Okay, can't we do this? R minus 2 cosine theta equals 0. Yes? So r equals 0 is one way to satisfy that equation, and r equals 2 cosine theta is another way to satisfy that equation. I just want to show you that this works, all right? What does r equals 0 look like? So remember, in polar, what you do is you start by standing at the origin, right? So imagine that I'm standing at the origin. The x-axis goes this way. The y-axis goes this way. I'm standing there. I'm just sitting there pointing out the x-axis. And everyone tells me, okay, we're going to plug theta in and then tell you how far to walk out. So right now, if theta is 0, look at this equation only. R equals 0. If theta is 0, how far do I walk? I don't. Okay, now if theta is 1, or let's say pi over 4, right? How far am I supposed to walk? This equation has, theta isn't even affecting it, right? It's like a constant function back in college algebra. Y equals 2. It's like no matter what x is, y is 2. Well, here, no matter what theta is, r is 0. So I'm sitting there, I'm like, okay, ready, go? No, don't go anywhere. Here? No, don't go anywhere. Here? No. Here? No, don't go anywhere. So what do I draw? A point at the origin. Is that point on that circle? Is that point on this circle? The origin's there. Okay, so I've got that point. Now, look at this one. Okay, I need to take a look at how we can get an idea of what this r equals 2 cosine theta is. I'm making a correction on the lecture video here because what happened was I told everyone that the restriction on theta was from 0 to 2 pi. It's actually not. Don't know why I overlooked this. It happens, I guess. So what I'm going to do is I'm going to make a quick little t-table to show you what this r equals 2 cosine theta draws. So if theta is here and r is here, if I pick theta as 0, that means that I'm pointing out on the polar axis straight out to 0 degrees. Plugging that in, I get 2 cosine 0. Cosine 0 is 1, so we get 2. That means if I'm pointing in that direction, I walk out 2. So I go 1, 2, and that puts me right here. Then if I do something like pi over 4, I have 2 cosine pi over 4. Cosine of pi over 4 is root 2 over 2, so I get 2 times root 2 over 2. These cancel. Root 2 is about 1.4 something. So what I'm going to do is I'm going to point out in the direction of pi over 4, which is about like this. I'm going to walk out 1.414, which should put me right here. And if I keep doing that and I do all the angles in between, I should start creating all these points along the circle. And you can see that my angle only has to go till I get straight up and down. That's at pi over 2. So at pi over 2, check it out. You get 2 cosine pi over 2, which gives you, well, cosine of pi over 2 is 0, so you just get 0 here. And that's why we're at the origin there. So our angle only rotates here through pi over 2. But we also have to go the other direction. We have to come down this way so that we can create all the bottom parts of the circle. We do not need to be over here on the left side. We don't have to point in this direction. So because of that, my angle, again, I said it was from pi, went up to pi over 2. My angle the other direction means that I should rotate negative pi over 2. So for that circle to be drawn, I need my theta to be bounded between negative pi over 2 and pi over 2, not 0 and 2 pi. So that means that my region D can be defined as all the polar points r theta such that negative pi over 2 is less than or equal to theta is less than or equal to pi over 2. And then my radius is going to be stuck between 0 and 2 cosine theta. So my radius is a function of theta. Now I can set up my double integral. So my double integral is going to be the double integral. I'm going to go from negative pi over 2 to pi over 2. And then I go from 0 to 2 cosine theta. And then I have in here the surface, which is, we're just looking at the top part of the sphere. And let me go back and double check my sphere. Where is it? We're using capital R for our radius of our sphere. You know what? I'm a little lost because I don't know what I did on this problem. I thought I'd used 9. Or, yeah, 81. So here it is. So I believe it's at 3 is the radius. So if the radius of the sphere was 3, then we would have 9 minus r squared here. And then we would have had the r, and then dr, and then d theta. So you have to figure out that integral. And I think in class I did that, and I had Mathematica do it. But that would be a different answer, and I would actually be just off by 2, because going from 0 to 2 pi is twice as much as going from negative pi over 2 to pi over 2. But that's neither here nor there. I just want to make sure that you get this major correction here on the restriction on theta. All right, sorry about that.